Well, me and Addie are going to see after. We're going to go see Florida. We want to go see after. I know, but we're going to see again. Really good. No, we're more in the literally, Addie said that she that you and her were going to. You weren't going to find it.
Like the time I wrote on the bunnies.
Okay.
Because I was like going to start here.
All right, so did you look at the last two? So like, look at this one. You've got this and this. What can you tell me about those directors? They're deactivators, and they're what kind of directors? Meta. But what are they to each other here? They are para. So how can we do that? Are you done?
I am.
Everybody get their deal on one. Did they get 4?
Katie did.
All right.
We wrote down about 2, and he goes, "Oh, we got 1."
Yeah, because they got 2 points and I got 1.
Be great.
Be grateful. It's all free.
Yeah, we're all.
All right. So how are you going to get 2 meta directives paired to each other? You already know how to do it.
Do it.
You already know how to do it. You may have an idea. Did you not work on it? Oh, what did you say, Stacy?
CH3 is an OP detector, so you start with toluene.
So if you start with toluene, and then what are you going to do? Okay, so how do you do that? What are the reagents? Help her out. Yeah. Okay, now that will give you both the ortho and the para. Okay, one nice thing about ortho and para compounds, unlike R and S, is that they can easily be separated. Now, how you would separate it, oh man, this thing. How you would separate them is going to vary depending on what you're making. So whether you would use, recrystallization, or you would use fractional distillation, or there's a variety of column chromatography that you could do to separate those, okay? But they can be separated. So what you can do here is, instead of listing both, you can list the one that you want. Okay? Does that make life easier? So you could just list the para one because that's the one that you want. That's a 3. Me and the pen are not 1. And today, me and nothing are 1. Okay, so now what am I going to do? How can I get to this? What am I going to do? Yeah, KMNO4 will work. The other one is the chromium, the dichromate acid. Okay, you'll notice that the KMNO4 one is usually written like this, 1, 2. The only reason is because the KMNO4 tends to work really well when it's basic, and you have to do that extra step to acidify it in order to get your carboxylic acid to be chromium. That's all. Didn't you do a separations lab last semester in the SEP funnel, and then you had to acidify to get the acid back? Yeah, so this is kind of the same thing. Okay, what about the last one? All right, I went too far. There we go. Here's the last one. What do you think about this one? This is what kind of director? OP. And what's this? Nope. It's OP also. And what are they to each other? Meta. Okay, so what brilliant ideas you got on that one? So we can do that one. Well, how are you going to put the chlorine on? How are you going to put the chlorine on? Okay, this is what we're doing. Okay, so you put the chlorine on with Cl2 and okay. How you put that on? How do you put that on? All right, so what are you thinking? I gave you that. What's the problem with that? Rearrange. Okay, so how can we do it so that it won't rearrange? Remember? Acylation. So that would be CH3, CH2, CH2, yes, Cl, and AlCl3. Okay, so what is that going to put on the ring? And what kind of director is that? Meta. Okay, so here's our benzene. Okay, so we're going to put that on. That's going to give us that. Okay, then what are we going to do? Okay, so how are we going to do that? Cl2 and FeCl3. That's a C. It just doesn't look like it. All right, and where is that going to put that chlorine? Meta, 1, 2, 3, 4. Okay. Now, what's the difference between that compound and what our goal is? So how do we get rid of that? Okay, which is? In HCl. The acid is essential. That's your source of hydrogen. Okay, so that will get you to the product. See how we did it? So are you getting the idea of how to think through them? Okay, so practice, practice, practice. Okay, you'll have some on the homework too where you slide things into boxes. On that sapling homework, if you haven't looked at it yet. And I'll give you some on the book. I just didn't get there yesterday. I don't remember what I was going to say. Okay, so we need a reaction. All right, so let's see. Okay, so here's going to be your answer choices. Let's see if I can fit them on here. I hope you can read it. Okay. You ready? Can you read them? This is a single one. This is bonded to this. See, what else did I do? Goofy. It's such a pain because I have to actually be like a half an inch away or a quarter inch away to get right on the line. Okay, so what do you think? Is there an option you want that is nothing? I could have written another one. I could come up with a billion possibilities. Take a guess and then we'll go over it. Got a lot of answers. Okay, so what does the chromium reagent do? It's an oxidizing agent, right? So it's going to oxidize what carbon? They have to be benzylic and they have to have one hydrogen. Okay, a minimum of one hydrogen. So this carbon has how many hydrogens? 3. This carbon has how many hydrogens? 1. This one has none. Doesn't matter if it has an OH on it or not. So this one and this one, the 1 hydrogen and 3 hydrogens, will get oxidized to carboxylic acid. Okay, the T-butyl group will not be oxidized. Okay, and yeah, if you went to all that trouble to put that isopropyl on there, you just lost it. Okay, it's kind of sad, really. Okay, that's what we did. That one we did last time. Okay, so elimination. Bulky bases encourage elimination over substitution. Remember that? So if you have this, I'm going to go like this. Okay, do you remember your bulky base? Oops. Did you find it? I'm just not organized like your bills for whatever reason. Okay, so I'm going to grab the proton. Where do these electrons go? In here, and then the bromide leaves. Okay, that's E2. Why does it say E2/E1? Do you remember what the E1 was? You go through what intermediate? Good review for the final. Carbocation, and so you could also have that bromine leave, and you would form the benzylic carbocation, and then lose a hydrogen from the methyl to make your double bond. So it's hard to say. It probably really does both. Some molecules do the E1 and some do the E2. Okay. So your product is going to be, what is that? What is that called? Yeah. Good old styrene. Okay. All right. So does that all ring a bell? Maybe a little bit. Put a little note down. If it doesn't, I better go look at last summer. Okay. Now, what if you want to reduce things? Okay. So remember that if you take a double bond and you add hydrogen, you reduce it down to the alkane, right? Okay. Well, benzene is very hard to reduce that way. Okay. It can be done, but it takes particularly high temperatures and pressures, like outrageously high. Oops. So you can easily reduce the double bond in the presence of the benzene ring, because being aromatic makes it so stable that it's much harder to do. Okay, so notice what we did. Okay, so if you took this compound, which has a C triple bond N, you can reduce that, and what would you get? CH2 and what? NH2. Okay, but the benzene ring remains intact. Okay, if you have to go up to at least 3 equivalents of hydrogen, like usually they would use excess, and then you would use high temperature, 175 Celsius. That's well over the boiling point of water or benzene. Benzene boils around 80. It's like double. That's how much pressure they want on the thing. And 180 atmospheres, and you could get it to that. But it's pretty tough. Okay, the moral of the story is that this is tough to do. I'm not hearing like the storm already, am I? Oh, okay, good to know. Good to know. Okay, so people wanted to reduce the benzene ring though. They were wanting to use it to put things around it in a specific order and then reduce it down. It's an easier way to make stuff. So this Australian chemist named A.J. Birch in 1944 found that you could use sodium or lithium in liquid ammonia with an alcohol and end up reducing some of the benzene. Okay, so we used sodium or lithium in liquid ammonia before. Remember what we used? Do you remember? Okay. Okay, and we were reducing it to a double bond, and if there's a choice, you would get trans. Remember, we used that to get the trans double bonds, okay? And so it was already in use, and then he decided to try it on benzene to see what it would do, okay? So here's benzene, and look what happened. Remember that this is like having double, single around the ring, okay? And we end up getting 2 double bonds in a ring. These are the 2 new hydrogens, okay? And notice that the double bonds are not conjugated. Okay, there's a CH2 between them, both directions. Okay, you with me? Okay, we're not going to do the mechanism. It involves radical anions, and it's really, really long. Okay, if anyone's upset with that, you come see me after class. All right, so here is a benzene ring, and it has an electron withdrawing carbonyl. Okay, so we have an electron withdrawing group on the ring. Okay, when that happens, the carbon that has it on it is reduced. Because you see, now we have two possibilities. We could get our double bonds here, or we could get them here. You see the two possibilities for your products. They could both be this way, or they could both be this way. So what happens is this carbon is going to get one of the hydrogens. So where are my double bonds going to end up? Here and here. And then I'm going to have hydrogens in those three spots. Okay, so it's going to look like this. That making sense? Okay, you'll notice up here they have this CO2 minus. That's because it's in a basic solution. Ammonia is a base, remember? And so it will be the anion until you go to the trouble of acidifying it and making it into carboxylic acid. So this would be like 1, and then 2 would be H plus. You would acidify it. Okay? You have to be careful what you acidify it with. You'd have to use sulfuric or phosphoric. If you use HCl, what will it want to do? Add across those double bonds. They are no longer stabilized by the aromaticity. Okay? And if you took this compound now and you added hydrogen with a catalyst, probably 2 equivalents or more, what are you going to end up with? You're going to end up with your cyclohexane. I'm going to acidify it. Okay? Is that making sense? So if you do this, that makes this DH. We'll keep doing that with carboxylic acids as we finish out the term. All right, so down here we have an electron donating group. Okay, so a carbon with an electron donating group is not reduced. So that means that the hydrogen is not going to go here. It's going to go to these spots. And your double bonds are going to end up there. Okay, that makes sense? So see what it looks like. Okay, remember that to begin with, each one of those carbons has only one hydrogen on it, except the carbon that has the group on it. Okay, that doesn't have any hydrogen.
Like you're only adding one of the hydrogen.
Yeah, right. One of these was already there. So when you do the reaction, you're adding, why? You're adding those two. Yeah. Okay, same thing up here. In this one, we added this hydrogen and this hydrogen, one of those. And notice they're always across the ring from each other. Okay, it's real systematic. You ought to be able to get it. Okay. All right, so now look at this one and figure out what's the major organic product for the reaction below. Now you get to do it. Because I'm like that. Do I have a 60? All right, so what can you tell me about the group that's on the benzene ring? What can you tell me about this? What kind of group is it? It's an
electron withdrawal.
It's an electron withdrawing group, right? So that means the hydrogens are going to want to go to here and here. There's already one there. Okay, and your double bonds are there in your product. So that is C. Okie dokie. Does that make a sense? Did everybody see it's between C and D? Okay. Okay, to reduce a nitro substituent, you can reduce it to an amino group by using tin and HCl followed by base. What is tin on the periodic table? SN. I don't ask those questions very often. Oh, yeah. You're like the number 10, no 10. Okay, so here's what happens. You use tin and HCl, and that's how you can get an amino group on your ring. It will be protonated after this step, so you have to deprotonate it by using the base. And you do it all in the reaction mixture. Like, you never isolate this. Okay, we just did it in an advanced lab. And you add the tin and HCl and you reflux it. And then at the end of the reaction, you add excess base. And then it's supposed to dissolve all the tin salts. Some people's work better than others. We're still figuring it out. All right, and then down here, you could also reduce it using hydrogen with a catalyst. But that is a little tougher. It's just harder to do. Although, I don't know, if the tin didn't work, I guess we'll find out. But we have a compound that has two kinds of reducing group. We're going to reduce them different ways. Okay, dokie? Okay, so now, do you have this in your slides? Tell me if you have it in there. I'm not going to go over it, but I want you to work on it. I think it's a homework. It's in your book. It's in your text. Okay, so what you want to be able to do is figure out the structures of A, B, C, D. And you have little hints as you go, because like here you have that compound. So does that help you go backwards and figure it out? Here's F. Okay, they call those roadmap problems. Okay, and so yeah, you can take a picture of it. I can post it too. You don't have it?
Yeah.
Okay, okay. All right, so I'll post it for you, or tell you what number it is out of the book, or you can take a picture. Whatever you feel the need to do. Okay, so diazonium salt. So once you get aniline, so you got nitrobenzene, you reduce it to aniline. You can convert it into an arene diazonium salt by treatment with nitrous acid. Okay, so what is nitric acid? Nitric acid is HNO3. HNO3 is nitric acid. Are you not finding that? Oh, I'm going to be sad if you don't have time.
No, we have this. It's by like.
Okay, okay. There we go. We're finding it. Okay. Okay, so now we're back on the same page, maybe. Okay, nitrous acid has a real different structure. HONO. So it's HONO. Okay, remember that nitric acid has that O minus N plus in it, like a nitro group. Okay, that's nitrous acid, okay? It's unstable. It's formed in situ. So that means that you put stuff together to make it. You use NaNO2 and HCl, and it makes the nitrous acid. And then you throw your group in, whatever your group is, your compound. Okay, we used to call that the HONO reaction. Get it? Oh no. Okay. All right. So what does it do? Well, what it does is it takes that NH2 and converts it into that. That is called a diazonium salt. Okay. Did you all do a lab where you made a diazonium salt, where you made methyl orange? Did you do the methyl orange lab? Okay, you made a diazonium salt in there. Okay, little did you know. Okay, and then you did something different to the diazonium salt. You can do a whole lot of things to it. You took another benzene compound and added to this nitrogen. Okay, that's not what we're going to do. We're going to lose the nitrogen. Okay, and the nitrogen will actually bubble off, and when you do these reactions, you can watch the nitrogen bubbling, and then you know it's done when there's no more nitrogen bubbles coming off. Okay, so what we're going to do is we are going to do the Sandmeyer reaction. Sandmeyer uses copper 1, cyanide, chloride, or bromide to replace the diazonium group. Okay, this is called nucleophilic aromatic substitution. It's not electrophilic aromatic substitution. Okay, number 1, there's no electron. We have a nucleophile, right? Br minus. Okay, we have a nucleophile, and look at what we get. We have substituted for the nitrogen, okay? But the key is we used a nucleophile. So our negative charge is going to go to the carbon that has the nitrogen on it. But the nitrogen doesn't just leave. Those electrons are going to go to the carbon next to it. So you're going to get an anion. Oh my gosh, I didn't leave myself enough room. All right, so let me kind of do it like this. Remember, there's an H there. I'm going to put it there just so y'all remember. And there's my negative charge. Okay, so then what's going to happen is that's going to go back to here. And the nitrogen is going to leave. Oh, my plus lost its line. Got goofy. Okay, that's it. That's simply it. That anion can be stabilized by resonance around the ring. Just like an electrophile, a plus can be stabilized by resonance around the ring. Only this time, when you draw your, and that looks like a plus, doesn't it? Oh my gosh, I can't win today. Okay, so when you draw resonance forms, you're going to start at the minus. Okay, and you're going to end up with minuses all the way around. Okay, so let's look at that so that you see it once. So here will be my, I'm going to put that H there. There's my anion. Okay, just to make it so that it's clear, it's looking goofy on that other page. So if you're going to draw a resonance, now you're going to go from there to there and out to there. See what we did? We're starting at high electron density. Last time, the pluses were low electron density, so we started at the double bonds. Now we're starting at the negative charge, that's high electron density. Before, the high electron density was the double bonds. All right, so what do I have now? So I'm going to draw what didn't change. Do y'all tell yourself that now? When you write stuff out, I'm drawing what didn't change. Okay? I didn't touch any of that stuff. Okay? So now with what changed, what do I have between here and here now? I have a double bond, and on this carbon, there's old Homer, I have a negative charge. I'll draw that hydrogen in. The hydrogen was already there. Remember, every one of these has a hydrogen on it. Okay, just one, and the top carbon didn't have any hydrogens on it. Okay, so can you draw another resonance form? So we're going to start at the negative, and we're going to go into that bond, and then these electrons are going to go there. If you didn't have the double bond there, you wouldn't get resonance. It would just be the negative charge on that bond. Okay, so what do I have? So first of all, draw what didn't change. Okay. Okay, that's what I didn't change. The blue arrows are where I messed around with stuff. Okay, so between here and here, I now have a double bond that looks hanky. If yours looks nice, I'm proud. And then you have a negative on that carbon. Remember, there's a hydrogen there. Those are your 3 bonds in your lone pair. Okay? Okay? That make a sense? Okay, let me go back because I had another example. Where am I going? My gosh. Okay, so here is using the copper cyanide. Okay, here's the copper cyanide. And so you're going to replace the N nitrogen with the CN. Here, I'll make them both go off. Okay? Exact same mechanism. No difference. The copper just kind of helps everybody along. We're not going to worry too much about it. It's called the Sandmeyer reaction. Okay, now, if you wanted to put iodine on there, they found that you didn't need the copper. Iodine is such a good nucleophile that it will work all by itself. Okay, you just add Ki, and the I minus will attack and replace the nitrogen. Okay, notice what is not the mechanism. The I minus doesn't go here and nitrogen leaves. You always get that stabilization. Okay. Now, note that KCl and KBr can't be used. They need that copper. And they can only be put on using the copper 1 salts. And these are nucleophilic aromatic substitutions. Okay? You have to have that good leaving group. If you just took benzene and Ki, you wouldn't get a reaction. Okay? Nothing will happen. Okay? All right, so what is the major product from the reaction below? Can you read the pictures good enough? Are they dark enough? That's Cl. Cl. That help? And all I want is the product after both steps. If this was on your reaction page, all you have to do is give me the product after both steps. You don't have to give me the product in the middle. Okay, it might help you figure it out to write it down, and I can understand that. But all I'm really looking for is the product. Okay. I'll draw up there what the product is after the first step and see how you do. It's 16, right? Yeah, there we go. Okay, so what is the product after the first step? After step 1. Oh, I don't have a thing. Okay, after 1, you're going to have, what is that? NaNO2 and HCl do? It converts the nitrogen to the Diazonium. Okay, and then what does the CuCl do? Replaces the nitrogen with a fluorine. Okay, what was the other one y'all picked? Was it this one?
D.
Oh, D. Okay, that's this. That's after step 1. Okay, if you want to replace the methyl on, or a hydrogen on the methyl with a chlorine, how do you go from here to here? What would you have to use? You'd have to do free radical halogenation from way back in the dark ages of August. Like, wasn't it that long ago? Maybe September, I guess. I don't know. We did it a long time ago. Okay? But it's benzylic, so it'll substitute readily. Okay? All right, so just keeping everybody on track. Okay, the Sheeman reaction is another thing you can do with these, and this lets you get fluorine on. Okay? There are a lot of drugs that work because they have put a fluorine in a specific spot. And so they really wanted to develop methods for doing that. And so this involves making the diazonium salt. So if you were going to make that, you would start with aniline and use the NaNO2 and HCl. Okay, and that'll give you the diazonium salt. And then you're going to add HBF4. Okay, I have never used HBF4. And what happens is you swap out the anion from chlorine for BF4 minus, and then you heat it up. So it's kind of 2 steps. One step is add the HBF4, and then the second one is hike the temperature. And the fluorine will come off the boron. Do you remember, what do you remember about boron chemistry? Remember that it was anti-Markovnian because boron was fickle. It didn't want to be minus, and so it wants to get rid of that fluoride because it wants to be BF3 and just be neutral. But oh my gosh, it only has 6 electrons. Oh my gosh. So that's why it tries to get 8. And so that's kind of the bizarreness of its chemistry. It's kind of fickle. Okay, so you end up getting fluorobenzene. So that's a way that you can put fluorine on a aromatic ring. Okay, not anything else, just an aromatic ring. Okay, now you can also make phenols. We haven't made phenols yet. Showed you how to make anilines. Okay, this is how you make phenols. You take your diazonium salt and you add water and heat it up and you get an OH on. Okay, it's also nucleophilic aromatic substitution. Okay, but water is your nucleophile and then you end up deprotoning. Okay, so basically they make the diazonium salt. They don't even isolate them. Weren't your diazonium salts real pretty? Weren't they like a real pretty red color or something usually? Was it not red? You don't remember? They're usually real bright colors, depending on what else is on your benzene ring, but oh my gosh, they're just really fun. Okay, so what I'm going to do between today and tomorrow, I'm going to record a lecture on carbonyl nomenclature. Okay, so be watching for that to be posted and watch over the break. Okay, and that'll, like I said, that's really going to be simple. So you guys will catch on to that really easily. Okay, I don't know if you could fast forward through it or not. You might sound like I'm shipping. All right. Y'all have a good holiday. Good luck on your lab final. I will see you Monday. And the pre-med